Okay, now, let's go Spencer. You've known Spencer by now. Welcome in. Tim Colonius as well, yeah, have a seat. And Juan Alonso. And we'd like to invite now Guilherme Silva from ATS, our sponsors this year. And Guilherme is an engineer specialized in CFD, works with ATS. He's joining us for the panel as well. Professor Bruno Carmo is our moderator. Thank you for sending in, contributing with your questions and topics. Gentlemen, our panel is, we go all the way up to 5 o'clock, or until the conversation ends. There's water there for you, but there's no alcohol, so I believe you there are 2 microphones on the table, okay? So whenever you think you should speak, you talk to each other and get a microphone, okay? Bruno has his on.
Okay, so let's start. The way that we are going to proceed here is basically our agenda. Following a suggestion by Professor Juan Alonso, I'll ask him to present the outcome of a very nice work that has been done by some members from academia and also industry, presenting the NASA Vision 2030 CFD code. And then I think we can go to a final discussion about this document. It's from 2013, right? 2014. 14, so it's pretty recent. And I gathered some of the questions that were sent to us, and also some of the thoughts of the organizing committee. And I grouped the questions, or the topics, I'll say so, into 4 different subjects. So modeling, numerical methods and tools, hardware, and CFD use. Okay? So we hope we can cover most of it. So ask Juan, please, can you come up and present the NASA?
Okay, so I guess the panel is to discuss the future of CFD as it applies to many disciplines, not just aerospace engineering. But we thought it was appropriate to tell you a lot about something that we participated in not too long ago. NASA, about in 2014, asked, 2013 I think it was, asked for somebody to put together a study to establish what needs to be done in terms of research in order to facilitate the vision of CFD in 2030 that would accomplish much more than what we can do today with CFD. And that came to be called the NASA Vision 2030 CFD study. So Boeing was the lead of it, so Jeff Slotnick was the technical person that was in charge, and Abdi Koudadoust was the program manager there. But many people within Boeing participated, including people like Venkat Krishnan, Philippe Spallard, and others. And then there were a number of people from Pratt & Whitney representing the aerospace engine industry, so airframes and engines. And then there were 3 of us that were, actually 4 of us that were academics. So Dimitri Mariplis from the University of Wyoming, Bill Gropp from NCSA. I don't know if people know Bill Gropp, but Bill Gropp is the father of NPI, this is what we call him, and he gets upset. Dave Darmafal from MIT, and then myself, and together we went through about a 1.5-year long process to think about what we thought will be the future of CFD, but more importantly, we held a series of workshops where people from academia, industry, government from the US and from the entire world were actually invited to participate. We did a number of surveys as to what people thought would be a very important set of research questions to be answered by the year 2030. And after about 6 more months of discussion and drafting, our report came out that was published as a NASA report, and that you can download off the web. If you just search for NASA Vision 2030 CFD code, you actually get the PDF of that report. So I thought it was maybe good to just tell you a little bit about it. This is a briefing that we gave to NASA as we were writing things, just to tell them what was coming. I'm not going to go through all of it. I won't tell you much more about the team and introductions, but this is what NASA had actually asked us about, and I haven't given this briefing in 2 years, so I need to see they wanted us to address the long-range planning required by NASA's, I guess, computational science programs inside the fundamental aeronautics program. They wanted us to give them a forecast of future computational capabilities required for turbulent, transitional, and reacting flow simulations. And they wanted us to talk about those capabilities that will help lay the foundation for the development of future frameworks, environments, physics-based predictions, enabling multidisciplinary analysis and design. So that's what was called for in the solicitation. There was lots of things in the study. I'm going to go through this because in just the 10 minutes that I've been asked to speak, I want to tell you that after all of this work, we made a series of findings, so things that we observed from the consensus of the community, and then we made a series of recommendations. I'm going to tell you just what the findings and the recommendations are. They touch upon a number of topics that I'm sure we'll be discussing, and I'm going to go to that. So let me just skip through some of these slides. As I had a bunch of questions, we can leave the slides with you. Oh, sorry, the findings start over here. So you can read the slides as well as I can. But I'm going to just tell you. So, first of all, NASA played a key role in the early development of CFD techniques. That was in the late 80s, early 90s. And since then, their investments have actually died down. So that investment in basic research on technology has gone down, and you'll imagine that there's going to be a recommendation saying you have to increase that effort to us. Okay, that was just political. By the way, NASA asked for this thing, but they've been using this report as an advocacy document to go raise funds to actually do more work with CFD. The second finding was talking about how hardware is progressing very rapidly and how the aerospace CFD community is not keeping up with the latest. And in fact, while many industry members and academia and also the folks at NASA have significant sized clusters, they're way behind the top wave or the front of the wave of the largest supercomputing capabilities that exist today. In the United States, that's typically the domain of the Department of Energy. So we talk about those things, and there was a lot of discussion about things that may happen in the future. And the chief scientist at NASA Langley forced us to put quantum computers there, although many of us don't believe that in the next 25 years there's going to be, or in the next 20 years, or 13 years I guess, there's going to be significant need. We did see that the accuracy of CFD needs to be improved, and it is currently hampered by the inability to reliably predict turbulent flows. This is transitional turbulence, etc., with particular emphasis on the capability to predict separated flows, so on and so forth. Incipient separation being one of the things that we were very concerned about. There was also an observation that the turbulence modeling community really has hit a plateau in industrial use for the last 15, 20 years. If you look at any of the industry and how they use RANS modeling today, those are turbulence models that were developed in the early 80s to the late 80s in some senses. Maybe the spot on Mars model a little bit later, but that was a 1990 or 1991 paper if I remember correctly. So it's very pressing to do something about the predictive capability. And there's been a lot of development in LES and DNS, etc., those are not ready to help directly industrial practice. So there's some cost estimates of one model LES, etc., etc. Then from an industrial point of view, mesh generation and adaptivity continue to be significant bottlenecks in the CFD workflow, and something needs to be done about that. I think Spencer mentioned in one of his presentations that these folks in mesh generation put themselves out of business, but now we are realizing that many things are not done yet, and there's a slight revival of mesh generation research. Algorithmic improvements are necessary, and there's a talk about mapping onto future computational platforms. Robust convergence is needed, improved scalability, uncertainty quantification methods, so algorithms for all those things still will continue to help out in realizing the Vision 2030 CFD, and there's some case studies. And then finally, we talk about the fact that the more and more we progress in CFD, lots of data is being produced, and we are not making complete use of all of that data in many different ways, and you can see some of the things that are being talked about as interesting things. Finally, even though it was a NASA's Vision 2030 CFD, there was a realization that CFD is just one piece of the puzzle when we're talking about aerospace systems. There are many other computational modeling platforms for other things that lead to multidisciplinary, multi-physics type problems. So there's a lot to be said about how CFD interoperates with other computing, models or computational models for various different disciplines. So you can imagine, or you can guess who wrote that chapter on that. So the Vision 2030 CFD actually came up with a number of different topics. So it's very heavily emphasizing the need for much more modeling in the flow physics, mostly focused on turbulence, but also in other areas like chemically reacting flows, heat transfer, constitutive models. There was a lot of talk about multi-phase flows that I know some of you are interested in. There was definitely a lot of emphasis in managing error and uncertainties and taking that to the next level. Much higher degrees of automation. The industry is obviously very interested in these things. Ability to effectively use massively parallel exascale type computing and beyond, fault-tolerant HPC architectures, so on and so forth. Flexible use of HP systems, so the ability for our software to run on the largest machines, exascale class machines, but also at the same time, a laptop or modest clusters with hundreds or thousands of cores, right? And then finally, the seamless integration. So that was the vision. There were a number of grand challenge problems to inspire people. They were not meant to be things that would be routine in 2030, but that would guide these efforts such that these things will be closer to being routine. 4 of these grand challenge problems that all have an aerospace flavor were actually set up. So large eddy simulations of powered aircraft configurations across a full flight envelope, off-design turbofan engine transient simulations, NDO of highly flexible advanced aircraft, and then probabilistic analysis of access to space, rocket launchers. So these were just meant to inspire the kinds of capabilities that will be needed in CFD codes if you're going to do these types of things routinely sometime around 2030, right? And so there's some discussion of all those. There was a roadmap created in terms of what needed to be done when, and this is a suggestion for the sequence, but more than anything, it was giving NASA ideas for elements of a research program that could be put together. I'll leave these slides, and these are public, so in fact, the report is better than the slides, and it's completely public, so you can look at it later. And then there were a bunch of recommendations. So I'll just read the top line for each one of them, but first, NASA, get your act together, start some more research and some real programs in CFD if you really want to have a chance of achieving that vision. So there's a lot of elements of what that research program might be. Second, we did think that NASA should maintain a simulation environment that research efforts across the US and maybe abroad could actually plug into in order to accelerate the development of capabilities and the transition of those capabilities to industry. The third thing is for NASA to make sure that it acted a little bit more like the Department of Energy, and that is that it acquired some of the top tier systems as the platforms continue to evolve, and that it made those available not just to research at NASA, but also to the research community outside. There was, oops, hit the wrong button. There was a requirement that in order to realize physics-based modeling, particularly of turbulence, there's still a lot of work that needs to be done together between computational and simulations, between experiment and simulations, and that we needed to make sure that a number of landmark experiments were done precisely thinking of the validation of these new predictive capabilities, such that you could actually have in 10, 15 years some more confidence in some of the algorithms that enable you to predict turbulence, separation, etc. Let's see. There's a lot of stuff about partnerships between industry, academia. That's motherhood of apple pie. There's some examples there. We also thought that NASA is beginning to lack the capability to implement such a vision. So they really need to get more people, and young people in particular, that have expertise in high-performance computing, physics modeling, etc., etc. And then we had a bunch of answers to NASA's questions. So effectively, the main slide that I did want to show is the one that you had here, which I will just leave up and stop talking in some sense. And it's the one that I think sort of outlines what we found were the key ingredients. So effectively, again, this was an effort by a group that was hired by NASA to do this, but it was also a consensus from about 150 CFD practitioners around the world. I'd say 2/3 from the US and 1/3 from everywhere else. And the key elements that we thought need to be addressed in the next 15 plus years until 2030 are the ones that are listed in those 6 bullets. So you guys stop there and just pass it along to some of the other panelists to see if there are any comments.
Okay. So let's go back to the table, please. So I have to say that many of the questions that the audience sent us are in line with those things naturally. Good for NASA. Yeah, good for NASA. So I don't know. Maybe we could proceed to the questions, or I don't know if you want to make a general comment about the effort as a whole, and then the discussion about the specific points to yeah, specific points.
I think it's the people part that's most important. I mean, Gerard and I are aware there's a couple of initiatives in the UK, and it's very much about encouraging what we're calling research software engineer and fellows of those. So maybe the people that design these tools, do they have to fit into classic academia roles? And if not, what do we do to build an ecosystem where they can design these tools? Back in the 90s, a lot of industries had their own R&D departments, and that's why there was such a vibrant community. Now those industries have tended to outsource that or use external packages, and so that's where this is the biggest shortfall, and I know that's been echoed in here, but we've certainly been discussing a lot in the UK. So we should strive more to support the people that kind of are contributing there and make sure they get recognised. And a knock-on consequence of that is, how do you get recognised for doing a bit of software development? We have a very clear environment. If we write papers and they get cited, then we get brownie points and big ticks. We don't have such a good system when it comes to software. So we should keep thinking about that and promoting that.
And in fact, I think people who develop software that is somewhat professional are chided in academia. I mean, it's more of a negative than a positive, I would say. So, I don't know what you're doing and what I'm doing, but it's certainly not helping. I do agree that it's about the people and getting the right people in and the right composition of teams to be able to use new architectures, get new physical models, et cetera, et cetera. And that's why there was a very strong message back to NASA saying you need to hire young people that have these skills. And secondly, there was a strong message to say you need to set up these programs so you can create the ecosystem within which academics, industry, and government people can actually interact. But that's always subject to both what the NASA folks want to do and what they can get funding to do.
I think it's a really great roadmap for the future. I mean, obviously, this is a CFD from the point of view of the aerospace community. I think multi-phase flows is a topic which is of enormous importance, and jet fuel even, I think the last time I checked, is a liquid, and somehow it escapes as a gas. So, we have an opportunity in the multi-phase flows that I think is a really unmet challenge in CFD. The methods that we have, the things that we can simulate are way behind what we can do for aerodynamics. So I would like to see that be an area of emphasis for the future. I completely agree about the people comment, inspiring young people to do interesting things in CFD and fundamental work, in addition to predicting very complex configurations. There's a lot to be done in terms of understanding fluid dynamics and flow phenomena. Maybe a negative look at our community over the past many years would be sort of constantly promising that the solution to everything is just around the corner. We have made enormous strides for sure, but if you go back many years, you see sort of overconfidence that we can tackle certain problems, and those problems that were allegedly solved a long time ago still come back to haunt us many years later when we discovered they weren't really solved. So, I would really like to see both in NASA and in the general community a real emphasis on fundamental research, solving fundamental problems.
Tim, I wanted to add one thing about recruiting young, new people, and that is a challenge today because in the, let's say, late 70s, early 80s, and maybe even the early 90s, there was nothing cooler than CFD, right? It was one of the top, research areas. New supercomputing capabilities were coming out that were making the pace of development of our capabilities much more rapid. It doesn't look good for young people when we've been using the K-omega model for the last 15 years, and that's what we can do in industrial practice. So we need to really look at step change capabilities in the basic and fundamentals of CFD so we can make the research field more attractive to that talent that's going to be needed to do those things. Because I don't think we know how to work do those things, to be honest with you.
So, Gerard, maybe I can ask for your, you have it.
Yeah, and just following on the comment back on people and training, and I think there's a number of things to recognise here. Like nearly all of the issues that were highlighted in this report are not exclusive to CFD. We're actually sort of seeing that right across the board. That's why even a lot of people you have, even in a department like Art Sciences, if they know partial dimensional equations and they're able to write some Fortran code, like they're on banks, so they happily hire them. So the fact is that these skills are not only in demand, but like the demand for people with those skills is exploding. So one of the discourses in economics, for example, is that we're in the middle of the fourth industrial revolution, and that pretty much translates to, well, there's whole books written on this, but the short version is if you're not highly skilled in mathematics and programming, you're not going to be employable. And then from my perspective, then the issue, and this has come up, like the one question that I asked in last week's workshop for anyone who's here, like there was a discussion about recruitment. And I think to think about recruitment is entirely the wrong way for us to think about the problem. The fact is that the people don't exist. And largely our job here as academics as well is to ensure that to create this workforce and basically provide the training so that we do create the people and create the environment for people with these skills. Because importantly here, we don't want, people aren't looking for computer scientists to solve these problems. They need the domain specialists, like the experts in CFD or other engineering areas, and they need those guys to be highly competent in computational methods. And how do we fix this? And the problem is that internationally, so I'm very careful here for what I say, this is an international issue. So in one or two conversations, people were talking about trying to attract talent from abroad, and that's entirely the wrong way to look at this, because everyone on the planet is trying to attract talent from abroad because the people that don't exist in the first place. And the fact is that our requirements are changing much more rapidly than our institutions. So in other words, actually the requirements for research and for industry and everything, they're evolving at a much quicker level than universities are able to react. And once again, this is not a comment about, for Brazil, this is what's reflected in all universities throughout the world. So the question is really about the challenge and also the opportunity for us is how do we take advantage of this? People talk about disruption. The disruption sounds like a very negative English word, but in enterprise is normally associated with the opportunity to make an awful lot of money and have great success. So really the challenge and the opportunity for us is to recognize, yes, these are immense challenges, and some of these challenges will require institutions actually to be reformed. The payoff is whoever accomplishes this is going to be a massive winner.
Okay. Thank you, Professor Gustavo. Thank you, Bruno. I'm glad to be here again after I had my PhD here in this school in 2008. So I'm coming back as an owner of a small company, technology-based, and we use a lot of CFD. But one thing about Brazilian market is CFD is not well developed yet. It's not like stress analysis. CFD is something like magic for some heads in the industry, And I see several roles here. You have the researcher that does the modeling, the numerical methods. You have the CFD, the implementation guy, the software guy that you mentioned, the guy that will take the best model, best numerical methods implemented in the code, because the implementation is not the numerical method. Implementation has some ifs, some matrix, assembling, so on. It's algorithms, and implementation is completely different than numerical methods. And you have the user. The user that, like myself, I took some time to understand that I'm a user. Because the CFD user would like to be a researcher, would like to be you. But the user needs to use what he has, with all limitations. You are using RANs. Okay, let's use RANs, let's solve the problem. Let's have some integral parameter to make the design something that is not too, how can I say, affected by errors. But you know that it's more or less correct. So, and you have the user of the user, the industry, the director that's demanding the work. So you have these four holes, and they are completely different. And some people doesn't understand that they are users, or if they are researchers, but they think they are implementation guys. Software is another thing. I learned that in my life. You need to have a version control. You need to have several things about software. Software is another thing. And that's my opinion. But anyway, just talking about Brazil, I think the academic here in Brazil plays a wonderful role because he's aligned with the top of the world. Our industry is not. You have a company like Volkswagen in Brazil. They don't do CFD. They don't do any CFD. They do in Germany, not here. Yes, we have Imperial. Yeah, Imperial is so fine. Yeah, I worked there for 10 years. Yeah, Imperial is an exception to the rule, and our company provides. We have 2 contracts with Imperial today. But anyway, that's it. That's just a talk. And I have another thing. I have other bottlenecks that maybe it's just mentioned in some slides here. That's CAD fixing. CAD fixing takes a lot of time. You take a CATIA model, it's 2 weeks to clean the model. It's too much. It should be automated. It's simple. It's simple to do some tool about it. And meshing is another bottleneck. It's still manual. We still need a good mesh. We still need a good-looking mesh. That's the solver. It's okay. The solver you can have any solver you want with characteristics that you pursue or you look for. But anyway, meshing in CAD fixing is terrible.
I certainly agree. I mean, we have quite a lot of discussions, Joe and I, and part of a couple of projects, about domain specialists. So you've got the code designers, and then you've got the software, and then you've got the HPC, and then you've got the users. And one of our challenges is to recognise those specialists and making sure they're interfacing effectively or have a clear understanding of how they talk to each other. But another domain specialist, which I think you touched on there, is who owns the problem of CAD fits or the mesh generators. Who often I feel sometimes in academia we're criticised because we come up with these schemes and then we're expected to translate it all the way to industry. And we're like, well, okay, our boundary has to come somewhere. We'd like to do as much as we can or deal with the research question. Where we lack, particularly in the UK, is a sort of governmental research institutes that might own that space. I mean, America's got a lot more labs, and you can see where some of the most popular softwares come from, because they take ownership of that, and they do the right software development, and they give it back to everyone. And where industry plays that role is another interesting question, because when there were these big industries and they had their own research divisions, they were able to do that. That isn't maybe so much the culture now. And that's why I feel there was quite a big hole there often about pulling these tools through back to industry and making them work effectively for the end users.
I think UK technological development program, they are very good because they involve academia, universities, small companies, and big companies. Big companies, they set the direction. I need that. The university works in the edge of the knowledge, and the small company, something like implementing some models or doing some code to put in the market. I have a company that's our sister company in UK, that's iChrome. iChrome is a spin-off from one of these programs with Airbus. And their software is used in Airbus Optimization Center. So I admire UK.
That's the good example.
Would you go ahead? I just want to add one point there. So, like, one of my passions is open innovation and open source. And I think one thing that, like, say, the modern, like, big surge in interest in deep learning and big data and everything is showing us is a lot of the very large businesses have got together to open up, have a base, basically open stack, and open source software, and like even they were open to their competitors, because really there was a recognition that, look, it's really expensive to develop this software. This software needs to be really, really good, and we build, like, where we're extracting value, we get it, like, we're taking it from the what we do with it, rather than the base technology, which is, like, too expensive to develop by ourselves. And I think it's interesting then when you say, well, why hasn't that happened? And then look at examples of why that hasn't happened in the areas that we're interested in, and indeed many of the things that are listed here. So mesh generation I have a particular interest in because I did my PhD in adaptive mesh methods. But they can go through the examples. Like, say, while a lot of the DOE labs, for the sake, like, let's pick up the United States for a second, but like they have been really excellent, like PETSI, for example, from Argonne National Lab. This is really an example, it's a cornerstone library for doing any solvers, if you want to invert a matrix. It's pretty much, if you're developing code yourself, you'll probably use it. It's really important. It's an open project, people get involved in it, it's an open team, they're very happy to engage, right? So this is a DOE lab, okay? And I think that's what we would like all the tools to look like. If we look at mesh generation then, the equivalent from the national lab, say, is Qubit. Okay, I think it goes by another name as well. Qubit, yeah. Qubit, yeah. This is corrected the Irish pronunciation.
I thought you said qubits.
And there it's interesting because, well, there's a lot of issues there that I could put, there's a lot of issues that they can't really open source. Well, there's elements of it that they're not able to open source because a big component of it is using proprietary engines for interoperability with file formats. And when you actually look up, it's well understood that the reason that you do have proprietary file formats, so let's pick on CATIA, okay, for example, but they're all the same. It's specifically designed to lock out competition, okay? So that's a serious problem for us because we're trying to develop new technology, we're struggling with these issues, but actually a large section of the industry is specifically, developing these proprietary products, like the file format. Like if you can't, for doing any simulation, if you can't read a file, you're pretty much stuck to start with. And even at that level, it's made for bird. And I think this is what we've been really wrestling with for a long time. And these are historical issues going back 20 years, and we're sort of stuck in this very sort of old mindset. While if we look at the big surge in data science today, shooting off ahead and it's leaving us for dead. And like it's interesting, like so a lot of these problems, like such as mesh generation and that, I don't think there's actually, it's fundamentally, it's not that hard of a problem. But the point about it is the community can't really play. Like pretty much you have to start and write your own code base from scratch.
I agree with you on that. I would hope there were some open stuff. You have to applaud the Gmesh folks and various other.
One thing I must say, so the reason that I wanted to get in that point, the most important thing is one of the reasons I'm here for the month is because I'm actually working with collaborators here at USP to set up a new research project with Shell. And actually nearly half of the project, it's quite a large project, half of it is only for automating mesh generation. So one of the reasons I'm so excited about the collaboration on that, and I think Brazil as well needs to think about where its big opportunities are, is because like there's no way I can like collaborate with anyone else that has got the same ability, the potential to hire a large team of developers to tackle this problem. And it is actually, like this is what we're negotiating and discussing at the moment. Like one of my particular passions is to make sure that it's open source, and then to make sure then that we're leveraging the entire expertise of the community to go and fix, like, you know, what is a fundamental requirement for our needs, and it's a bloody pain. Like, you know, we want to solve all these fancy flutes problems, and we can't even create a mesh to start off with, or fix the CAD or whatever. I see these as fundamental things. So one of the reasons I want to bring that up is because we'll be trying to recruit lots of people. So if you're looking for a job next year, keep us in mind.
So, several comments. I agree with the importance of mesh generation and the lack of attention it's received. We may get back to it. I also agree with the importance of open source for more rapid development. I not only agree, but I think I practice what I preach in that respect. But I wanted to get back to something that Guilherme has said, because I think in order to realize the future of CFD in aerospace and in other disciplines, you have to have the component you're talking about of industry maybe driving some improvements that are needed. But that's typically going to lead, if you leave industry alone to its own devices, it'll lead to process improvements, shortening of the time, but it's not going to lead to a step change in capability. So if there's one regret I have from the NASA 2030 CFD study, is that even though we didn't push hard enough to give it a bit more of a flavor of the fact that in order to realize significant improvements in geometry, in mesh generation, in algorithms, in parallel implementations, in physical modeling, you really have to focus on fundamentally different or fundamentally better ways of doing things. So you can't leave just everything to industry to drive, otherwise you're going to do some things you know how to do today very fast.
Yeah, I was just talking about the program that's on UK.
Yes.
I was just talking about a research program in UK that big company drives the development, but I'm not talking about everything. Okay.
So taking the first topic that was our audience required to be discussed, I'm going to put all the points here, and then you choose one. So 4 points that we have in home modeling, the classic double-S modeling. Double-S modeling, what's going on the trends for the next decade, let's put like that. So LEF, ES, so both academic terms and industrial terms. One thing that's not really solved yet, transition. Transition is another really hard problem. How to deal with laminar and turbulent flow in the same domain, the same simulation. We have some modeling for that, but still I think it's lagging behind the turbulence model. Other challenge that we have in the fluid flow alone, like boot phase flow and acoustics chemical reaction. What are the big next challenges for the next decade in terms of physical phenomena? And also some of the new trends in numerical simulation, getting away from next navigation equations, trying to do all this stuff to simulate fluid flow. Put 2 examples there, but if you have others, that would be welcome too. So lots of Boltzmann methods, and also using some machine learning to produce order models. So, if you would like discussing any of those points, please take the microphone.
Yes.
Well, I would say something about turbulence modeling. I think maybe the way I would see the next decade, and maybe even further into the future, is that instead of thinking about this long list of acronyms and saying which one is going to be the right one, we'll be in an environment where it's easy to run all of them on any given problem. People like Juan will come up with clever ways to have adjoints that tell us which model is doing the best and agreeing best with some limited amount of data, for example. So I think, I think for some people, maybe turbulence modeling is like a religious belief of you have the Navier-Stokes equations, and that's a description of the physical process. A turbulence model is an attempt at a shortcut, and it's not clear that there exists a shortcut to this solution, right? You're making an approximation always, and you have to live with an error and an uncertainty. So I think we have to accept that there may not be a universal turbulence model that's going to work for every situation we come up with. We have a number of really excellent models considering what they're doing. They're phenomenally good models. But we need to learn to use them, not just one, not just our favorite one, but really all of them, and new ones that come along, and look at getting data. If you're in the industry and you need to predict a design, oftentimes you're working with trend-wise predictions, and it won't maybe matter which of these models you use, right? If you're looking for precise agreement, then I think you have to run them all. That's my sense.
I'm going to second that. Let's stick with turbulence for the time being. I agree. I think we are on the verge of routinely being able to do a number of additional models of turbulence beyond Rand's models, right? I call LES a model of turbulence, right? I call DES the same. I do think there's some fundamental problems, though, for industrial applications, so relatively large Reynolds numbers, so I'm going to sort of betray my own interest. It's really aerospace in some senses. I mean, we know how to do LES, but we cannot do the Reynolds number we want. We know how we can do some wall models, but we don't really know exactly when they work and when they don't. But more importantly, when we do wall model LES, we don't know what to do with the upstream laminar portions of the boundary layer that maybe drive the cost of the computation. So I think I second your opinion that we need to look at ensembles of these types of models and automatic ways of deciding when and where to use what. But I do think there's some fundamental improvements to some of the models that we have today before they can be routinely used by industry. And I think we need to push for some of that research to take place, such that then somebody like me, for example, who's not a developer of LES but maybe a practitioner of it, can actually put them in some codes that may help bridge the academia industry environment. But I'm with you, and this is, in the NASA Vision 2030 report, this is the strongest point it's made. We really have a small.
I partly agree. So I definitely agree with the starting point. So I deliberately kept away from turbulence modeling throughout my career. That's kind of what's been a mission, and I've nearly been drawn back into it with this more recent stuff. And I point out in the fidelity modeling, yeah, we're doing exactly that. We're starting with RAMs, we might use that as initial condition. Bench, if we use a wall model LES as initial condition, it takes ages to establish these flows. Ideally, they need to help ventilate the car, we can't afford it. And if you take that model and they're uncertain about it, and then you put in a higher fidelity model, you see where it drifts away. And that gives you some sort of sensitivity information, if that's very naive. But in that strategy, we're choosing to change the fidelity of the modeling, not the turbulence models. So what I don't fully understand is, are we truly at the boundary of, there's a level of error that goes with the turbulence model, and is there truly one that's going to improve it? Well, so we are changing you're changing the fidelity there, but I'm not saying you can suddenly come up with another turbulence model that's going to improve the first step. Using the different fidelities might be the solution, not going back into turbulence modeling as an improving. Yeah. Or you may well inform a RAND model with a high fidelity, but that's using a different level of CFD solution to come back to it, not trying to sit of, okay, here's another strain-stress relationship that I can think will be better. Yeah. And so that's the trend I see happening for us. I don't know if that's going to carry on, and then and we used LES just once here, but there's a distinction we're tending to draw now in the UK and something called the UK Turbulence Consortium. It's more modelled and more, whatever the other expression is. Yeah, I hesitate to say more resolved because I know our stuff is not more resolved, but I sort of more capturing, seeing the boundary there versus not seeing it is kind of where maybe the main distinction is being drawn, because that's where it gets expensive once you start capturing the boundary there. You can probably afford to do some sort of unsteady RAMs or an LES. That's the kind of the industry standard. So that's the point we're at. The question is, so I was confused when we said to put more investment into the research into that, in what sense? Because in the 90s, a lot of people developed turbulence models. Some of them are my colleagues currently, so I'm quite familiar with the debates they had and they carry on to have, but I don't know if there's much more environment for that to carry on versus us taking. If I jump to the end point, the reduced order model of machine learning, there's a lot more exciting activities in data assimilation. How do we take some information that came from experiment? How do we take any source of data and feed that back into our modeling? And maybe that's how we unleash the next step.
If I may, I do consider LES a turbulence model, I think, but it's a very different turbulence model than RANS models. So the comments were addressed not at developing necessarily new RANS models from first principles of the introduction and destruction terms, but rather at new LES, full model LES, etc. models. And also, as you were saying, I think there's a big opportunity to take higher fidelity data, let's say bulk resolved, if you want to call it that way, LES and others, maybe DNS data, and using some learning techniques to complement or enhance RANS models, so you could have models that have broader applicability, right? The thing we suffer most from in RANS models is that they work really well for all of our cruise conditions, but they don't work anywhere beyond those cruise conditions. High lift, Buffett situations, maximum Mach number, Dipont numbers, things of this kind. We know that the separated flows are not always predicted well, and we can miss the actual loads by a factor of 2 easily. So when I say fundamental research in turbulence modeling, I was going beyond that.
About turbulence models, I have a question for you. That's for you four. Because I'm a user, not a researcher. The turbulence models for me, I agree with you. LES is turbulence model. The RANS is a filter in time, and LES is a filter in space. And the problem of LES is basically fundamentally the same than RANS. That's the dissipation. Are we ready to model dissipation? Are you ready to understand the second law of thermodynamics? Basically, it's that. All, including Lutz Boltzmann, which is there, which is LES with no mesh or something like that, they fail when they describe the wall. They fail when they describe the subgrid turbulence model. So, that's my question.
I have the microphone. Unfortunately, and I'm not sure that I can answer the question. I mean, I do think that LES is a turbulence model, certainly, and I think, in a sense, DNS is a turbulence model, right? When we were first doing DNS, 30 years ago, we didn't know what resolution was required to fully, quote unquote, fully resolve a turbulent flow, and it turns out that the resolution requirements are not as bad as anybody would have predicted based on, say, the Kolmogorov scale. You can get away with quite a much coarser description, and there are all these odd things that happen in turbulence, like a 3D turbulent flow it requires less resolution than a corresponding non-turbulent 2D flow at the same Reynolds number. So turbulence is here with us. I think we would be foolish to invest in ideas that were somehow going to create the magic turbulence model. LES is a filter that's applied to the equations. I think we should concentrate more on using data. This was said. I'm not sure who said this, but using data in a much deeper way than simply comparing our plots with experimentalists after the end of the project, right? And then assessing blame and going back and so on, right? we need to be right there together, measuring, computing, pulling these things together. Maybe the turbulence model isn't so important if we go down that route. And I would just make one more point about turbulence modeling. And it's there was a comment earlier about the numerical methods, not being so important. And I think that's true. That's largely true for RANs, certainly. I think with LES and DES and any of the hybrid sort of formulations, it's not really true. The underlying properties of the numerics have an enormous impact on the way the turbulence model works. And all LES are not created equal, right? There are some algorithms that are much, much better than others. I think, maybe if there was a challenge for young people, I would invite you to think about the following, right? Discretizing the equations of motion is itself a model. And the turbulence model, if we approach that from the same point of view as a numerical modeling exercise, as an approximation theory exercise, we may make further progress that we won't make if we have an eddy viscosity for forever and ever, right? That was a concept that was invented a very long time ago based on an analogy that's a useful analogy, but it's not a numerically precise one. So, I think there's a lot to do in turbulence modeling if we kind of go by that framework.
Tim, I'm going to agree, but I'm going to also tell you something that Dimitri Mavropoulos and I discussed a lot and did a little bit of research while we were writing that report. And that is that the numerical algorithms are not only essential to describe the equations, whatever model you end up settling in, but in addition have been responsible for somewhere between 40 and 50% of the improvements in time to solution for RANs in complex configurations. So we all think that it's been the computers that have given us that capability, but when you actually look at, we looked at around the 1980s, early mid-80s until about 2015, and in there we could ascribe about 40 to 45% of the improvements in time to solution to the actual numerical algorithm and the rest of the computer, of course. So I think numerical algorithms are not only necessary for these types of better descriptions of the actual models themselves, but in addition, in order to make sure that you can continue to do these things in finite time, despite the fact that you may have an exascale computer. It's not going to solve our problems by itself.
I want to follow up on 2 points. Just follow up on that one immediately. I think this is something that's frequently not understood very well. Like very often, particularly when people are talking about new computer architectures and optimizing code, the expectation is that you hand it over to a software specialist who specializes at making code go faster, and you think that's as good as it can go. And that's a really big mistake to make, because typically if you already have a pretty reasonable code and you throw your ninja hacker at it that knows everything about the silicon to make it go faster, like those guys are already presenting a journal paper at a conference if they get a 10% improvement of performance. The reality is you only get a major increase in performance when you change the algorithm. And so I think that, and this is one of the challenges as well when we talk about recruitment and training, training people, is you're not off the hook just because, you live at one of these levels. In actual fact, the people who have the insight to the modeling and then at the numerical algorithms, those are the guys who might get you 100 times speed up or larger just because of innovations in algorithms, as opposed to someone who can only hack around at the implementation after all the interesting decisions have already been made. So that's the one point.
I teach a class in parallel computing every 2 years at Stanford, and the first thing I tell the students is that a bad serial algorithm implemented in parallel is still a bad algorithm.
This is really important. I think for anyone that wants to argue about that, just compare doing a cross correlation with and without Fourier. There's a factor of about 200 in the difference. Okay, and this is true for everything. But the other point then is, I think the other challenging for everyone, ourselves included, is, and I think when we talked about data, we were sort of getting there in terms of being more creative about using data to enhance our modeling capability. But I think we can step back and think about this more generally. The correct way to think about machine learning and all these trends is more about machine-human collaboration. So and I think we might start like fundamentally rethinking how we approach modeling. So if we even think about something like turbulence and experience choosing the appropriate model, you might start, and we talk about cloud, well then you might imagine platforms that thousands of people are using, where actually experience from the entire community is being learned by the algorithm. So this is exactly what radiologists do already in terms of having a human in the loop to improve the success rate of radiologists identifying cancerous cells and mammograms. It's the exact same, from an algorithmic perspective, it's the same process. But then also, of course, you need data provenance and all these other issues, but there are software engineering issues that we know something about, but also you can be using that. And we also know then from big data, the crucial thing is to have lots of data. But we do software, we do simulations, we generate petabytes of data if you actually think about the aggregated, what people are doing in the world. So I think by just simply move, and as well, other people in DOE labs and whatnot, they're doing high fidelity simulations that are just crazy high Reynolds numbers at very high accuracy. That's actually all raw data that can be used to create submodels, reduced models, which are also could be machine learning, call it what you want. They all basically, it's all interpolation and approximation. But there's a massive amount of data there, and I think unless we need to move away from the idea that we're one guy in a lab with our workstation swearing at the computer because we can't get our solution to converge, and more think about what's the global trend in technology, better integration and and extracting more value out of everyone's experience. So again, the challenge is, particularly for the young people who are looking to to do something interesting, stop doing what people already did 20 years ago, because guess what, it's been done. It's not going to make you rich or famous or anything else. I think the real challenge is, I think we're living in extremely exciting times from a technological perspective. We've never seen such a rapid rate of disruption of technology, particularly in the software sphere. In terms of computing, you've just got a stupid amount of compute available. But you'll find if you have a good idea, you'll find people will give you supercomputers for free, readily. So the question is, stop trying to do what people have done 30 years ago and redo it again. That's not research. That's called a tutorial. But instead, start thinking about what are you going to do that's going to be new and interesting and innovative.
If I could, I'd like to amplify that point. I think it's very important. So expert systems would be one way to think about this, right? So CFD practitioners are, I'm always amazed at the extent to which it's an oral tradition, right? You can't read papers or books and figure out how to do a proper RANS simulation of a complex geometry. You have to work with people who have already done it, learn how to use the software, learn how to use the tricks, and so on. The system tells you nothing at the end about how good the answer might be. And in many cases, we don't need complex uncertainty quantification to know when a RANS model is not going to be very accurate, right? I mean, if we have a separated flow, we know RANS is not going to be very accurate, and there's no reason that Fluent or OpenFOAM cannot detect a separated flow region automatically and warn a user that the RANS model is not likely to be very accurate in this scenario, right? And if our codes have these features, right, then the engineers using them wouldn't be tempted to believe them as much as they do, right? And I think that would be a real advance for industrial practice of CFD. We need to take all this knowledge that we have that's passed down as a strange oral tradition, and we need to turn it into a software product, right? We need the Google of CFD to answer the questions for us, rather than having to learn them in a strange process in a university laboratory.
Regarding the industrial use of CFD, we did a case last year about a simulation about the wind over a ship. And what's about this wind over ship? is because each ship has a structure, different structure. So, and it calls vortex, flow detachment, different one of other. And you have a helicopter landing. So for each ship, you need to have a flight envelope for landing because of the vortex. Despite we didn't simulate every turbulent structure or every vortex, we looked at a parameter like a CV, it's a local speed over the free stream speed, and it matched. We could use the data to determine the envelope. So, for one side, I see your point, but for the other side, we do have some CFD tools that can solve the real problems. Because with some engineering, you can make it some assumptions and go ahead.
Okay.
Well, let me just say, I mean, I agree with you completely. I don't think these are separate things. I mean, maybe I didn't make my point well. I mean, it wouldn't hurt in that process that you were going through to have the code tell you that you should beware of the results there, right? And probably you knew that. But you learned something in that process, right? And that now is something that the engineers in your company are going to bring forward in their experience, right? But the rest of the world, except those people in the audience here, are not going to know what you learned. They're not going to know that CFD of this ship worked and so on. Maybe they will in your case, but you know what I mean? My point is that we need to find ways to automate the sharing of knowledge in CFD.
And I'll go a bit further. The reason I think you can see the answer Tim was suggesting, you can't see separated flow, it's just about smooth and fixed separation. But you've got really fixed geometries, doesn't matter the codes, they know where to separate and it gets the right value. If you've got an aerofoil, sudden angle attack, transition point can move 50% of the chord, it will get it wrong. So again, it's taking that knowledge. I knew that's different, and being able to impart that to everyone else and making sure they know when they've got this problem, yeah, they're fine to use the round one. They don't, okay, you've got to use a better fidelity model.
Just my point is, I know what you're talking, I agree with you, and I know that the flow is not correctly simulated. And as a user, I know that the software has limitations. If my customer asks me, describe the vortex here, no, I won't do it. Because the software is not implemented for that. I cannot describe the vortex here, but I can guess what the speed right here, what the speed right here, what the speed right here. Maybe in some point, like very close to the flight deck, I did get the points correctly because of the vortex. So I can explain this point, I will not make it match. I will not spend 2 years in a project that is 3 months, 2 years by free working, just to explain one point.
We want to make your job easier.
I think, sorry, let me summarize that. What we're all agreeing to is that the fact that a CFD solution is not perfect doesn't mean it does not add value to an engineering process. But it doesn't take away from the fact that you have to know how imperfect that CFD solution is so you can carry on with your engineering processes knowing the consequences. So now let me turn the conversation back to innovation in CFD because I think certain things were said. Tim is absolutely right. You know, we can't think about just incremental improvements in CFD codes. You know, we've been talking about agiles and error estimation. Why don't we have CFD codes that don't have you do any of that? But instead of just telling you what the drag coefficient is, it says drag plus or minus X automatically without you thinking about it. If in 30 years from now we're not doing that, when there's already a solid theoretical foundation for this, we will have failed. So for all the students in the audience, you got to focus your energies on making, for all the student researchers in the audience, you got to focus your energies in making these new qualitative differences of doing things become commonplace. Now, right now it takes, like I'm saying, a highly skilled researcher to maybe an adjoint solution and then do some error estimation or to put some error bars that may or may not. You have to be thinking about the fact that this is going to be an intrinsic part of the CFD solution, and the mesh is going to be adapted all automatically, and that you, the practitioner, are not going to know what's going on behind the scenes, and that is fine. So innovation in that respect, I think, is critical for more widespread use of these types of solutions. And you may tell it, just give me a rough answer, because I'm just starting. Later on, I'll ask you. In terms of innovation, I want to say something about using data in order to infuse models of turbulence globally. But let me focus on Rand's models, because Rand's models get a bad reputation. But the Reynolds averaging process of the Navier-Stokes equations, it has nothing wrong with it. It's an exact mathematical transformation. What's wrong is that there are certain terms that need to be closed that people have come up with. But the transport of various different quantities, the dissipation, the diffusion, that's all fundamentally correct and needs to be reused. So Rand's models are very good in some aspects, typically the left-hand side of the equation. In the right-hand side of the equation is where you have all the models. So we spent about 4 years. So I had a student, Brandon Tracy, who just finished, and I think maybe Carlos knew, who was co-advised between myself and Kartik Duraisamy, who's now in Michigan, and Philippe Spallard from Boeing. And in there we started asking these questions. What if we had more data? We have a Rand's model, it's a Spallard-Mars model. What if I didn't know the right-hand side of the Spallard-Mars model at all? But I knew that there's some, that's not the best example, but I knew that there's some transport and diffusion parts that are correct. Can we learn it from data? And it turns out that it seems easier, the concept is very simple, but after you pose the problem properly, you can actually learn that model from any instantiations of running the correct Spallard-Mars model. Not only that, but then you can extrapolate to other flows. So we're trying with K omega and various other things, and using LES data, et cetera, et cetera. I think correcting those aspects of Rand's models that are not exact, that are not mathematically correct, can be done with certain amounts of data. And I think that's a really attractive research area where we don't have all the answers, but that maybe would help expand the applicability of these Rand's models. So I'd like to put a word in for that. So.
That could come from other fidelity talks. That's what I mean, in some sense, it's happening through the people. We talked about this curvature correction model. They realise you have an energetic vortex, you go back and correct it. We just need to take the person, go towards the data, and make sure that's good.
Thanks, David. So when this student was doing the study, we were trying to see if we could reproduce the Spallard-Mars model. Philippe Spallard was on our weekly telecons, and we joked with him that the title of the next paper should be, "Do we need Spallard in these Spallard-Mars models?" And he didn't want that title. But it is true, because what the human has been doing is taking a bunch of model problems, some information about how turbulence behaves, and trying to come up with some functional fits and coefficients in order to describe a subset of the problems of interest. This is how the Spallard-Mars was created. You cannot tell me that an optimization, fitting, or learning algorithm, whatever you want to call it, infused with enough data and with a learning problem posed properly, cannot do a better job. You can learn the coefficients much better, you can learn the functional dependence much better, you can expand the range of all those coefficients and all those solutions much better. It's something that's going to help. And it may not be the full solution, but I think it's going to improve some of the Rand's models significantly. These streamlined curvature corrections, or even just realizing that many of these turbulence models have destruction terms that depend on the distance to the wall, and that doesn't apply in the middle of a core that goes 20 span lengths behind. I mean, those are very useful insights, and you can take them in, but then you can enhance them with data learning techniques.
Okay. Suggested to move on to that's very interesting. It's a very interesting point here. Okay. So numerical methods and tools. So some of the points have already been discussed here. So first of all, what's missing from commercial software to incorporate some of this that we have been using in academia for some years already. Examples, high order methods. Examples. Another example, joint solvers. Okay. Big data in post-processing is another challenge. So that's another more specific question as well. Should we invest on large step implicit methods or highly parallelized explicit methods? And that's the question that I think you have, especially for my friend there on the tip of the table. Computing language platforms of CFD development. So how can we improve that, the learning curve of using as CFD software or implementing something new in the CFD model? Take a peek.
Hello. Just one thing about the transition model in the other slide. I was waiting for that subject. It's one of my subjects that I studied during the PhD, so the only subject I can talk here. About the transition model is pretty standard today. You use like the transport of gamma intermittence and transport of Reynolds theta. But Reynolds theta is empirical formulation inside the transport equation. So what is missing there is the trigger mechanism where the spots start, where these turbulent spots start coming. This is fundamental, and you have linear theory about that, but linear problems are a small part of the whole problem. You can imagine that I worked with a wing, with a heater, anti-icing, droplets impingement, film formation, breakdown to rivulets, and all this is a complex system that made the transition coming upstream where it was supposed to be. So I started to study transition. Luis, who is in the audience here, who works for Imperial today, study here also in these transport equations. But anyway, my thought is how far we are from predicting the beginning of the spots. I'm talking about beginning of the transition region, not the full turbulent. So between the beginning of the spots until the full turbulent, you have the turbulence development, which is another problem. Okay.
I want to answer this, but I can't answer. I can have a go at sort of answering that. I mean, I've been part of a 5-year program on lambda flow control in the UK in terms of modelling. It was quite interesting things. I hadn't done a lot of transition before. Sort of these older guys through asymptotic theory, and then how to improve the prediction capabilities. And there are these E to the N techniques which also feed in and are often criticised, but we don't know what else to do better about that. I think, in a way, for the next 10 years, some of the solutions we mentioned, capturing just a sort of the clear understanding of data that's out there and bringing it to the model. I mean, there's lots of understanding of receptivity in isolated problems, but there's not any, we don't bring it all together and then we don't use it in a kind of more industrial sense of how we apply it. So the tools, there's PSE tools.
You would have also a disturbed laminar part.
Yeah.
You have the laminar, disturbed laminar, and transition region.
Yeah, so the bumps, gaps, junctions, stuff that all triggers that. And that's the linear regime. So I think the theory is kind of there, but our adoption in terms of practice, industrial practice, has been slow and convoluted, and our discussion on use of data might be one of the solutions. In terms of turbulent spots, the thing that's happened, and this is much more at a fundamental level, it's a lot more understanding of the edge of chaos state. So these are solutions to the Navier-Stokes equations that represent these trigger points. I don't yet know, I'm not aware of anyone that's worked out how to bring that into modelling. But in terms of the fundamental fluid mechanics, our understanding, I think, has moved forward quite a significant stride. Where you bring, so the challenge out there is how does that come into our modelling and our industrial practice? That's now what's going to happen. So linear transition, better data, better usage. Non-linear transition, okay, some theories come out, and we've got to see how that comes into our practice, and then we can perhaps move forward.
Okay.
I add to that before we please Bruno, we jump into this one? So, I think, let me just make a provocative statement.
Sorry for that.
No. Let me just make a slightly provocative statement. For me, transition is like cancer. You know, let me explain. Cancer is a word people use to describe some phenomenon, but there are many different types of cancer. And transition is just the same way, and I don't want it to have a bad connotation. You know, people talk about transition, but there are many different ways of getting to transition. So I do think that with well-resolved large eddy simulations, we are doing a fairly good job at so we have reasonable models, but not very expensive, to predict transition. So I think, you know, using those models, making them more effectively, and perhaps complementing with data is not a bad plan to go forward with transition. So in my discussion in the previous slide, whenever I talked about turbulence, I kind of inherently was talking about transition as well. So.
That was my initial plan. Of course, it's higher order methods, but I actually want to go to that third point there, which I think is the more interesting one. So there's large time step implicit versus highly parallel explicit methods. We've talked a lot about all the changing architecture out there and how we're going to embrace it. And the most straightforward, simple thing to do to embrace it has been to use explicit methods. And the successful codes are generally doing that. But we haven't been very forthright in admitting that our time to solution hasn't been improving for that. So at the same time as we're using explicit methods, our time steps have been going down just as quickly as our speed-ups have been happening. And I think we're kind of on the cusp of that now. So the sort of Gorman Prize this year, one of my colleagues has entered, it had a very good code and it was very impressive, but they gave the prize to this Chinese group who had managed to work out how to have less petaflop usage on this machine, but to have an implicit solve. And their argument and why they allowed that to win was because in the time to solution will be better. If we can take big time steps still, we're going to get an answer that's useful for industry. And it just represents a natural evolution that we have to work out how to go back and look at algorithms that work on these architectures that solve rather large coupled systems. And when we do that, we'll truly be using the new architectures. And so, we'll have some ideas of what we might try, but I certainly have no solutions at this point, and that's definitely a sort of juncture of the generation of the audience that's going to see happen, and when we work out how to do it, and we will see significant improvements for computing or time to solution.
So I agree with you. I think we've been sweeping that under the rug. It needs to be looked at. I'm very concerned about the fact that when you go to these implicit algorithms for time stepping or semi-implicit, you end up making the job of the programmer light of this new architecture is impossible. I think that's another one of these areas where the human programmer, no matter how talented he or she is not going to solve that problem effectively. So we've had the benefit of, I would say, almost 20 years now of DOE funding through the ASCII and PSAP programs, and we have an ongoing project now. For the last 15 of those years, we've been working with our computer scientists. And, you know, we humor them for the first 5 years because we knew it was just pie in the sky, it's never going to be used. About 7-8 years ago, we started developing with them a domain-specific language called LIST that, you know, we now have something called LIST too, and you guys have been doing similar things at Imperial. The latest thing that I see that can have significant impact in how we implement these algorithms on highly parallel machines is the fact that we can program our computational tasks in some ways that restrict a little bit what we do, but still allow generality, but enable program analysis by computer science, not by computer scientists, but by computer programs. And then runtime environments, and these hierarchical machines decide where to put each of these tasks, depending on the type of task, but also data references that it does. So there's something, an effort by some of the computer scientists that we're working with that's called Legion. Go to legion.stanford.edu if you want to learn more about it. Where indeed you express your program in these types of tasks with data regions. That's where the Legion name comes over. And then there's about 10% of the machine that is being used not to do computations, but rather to stay 5 or 6 iterations ahead of the program to analyze where each of the tasks should actually be sent. There's these macro constructs and decide where that goes, that are assisted or not assisted by the computer. I think as we move forward, these algorithms will only be implemented appropriately in those machines if you have some of these runtime environments. For me, I've exhausted my capability of, in my head, doing load balancing of complex algorithms that have different costs for different elements, different orders, than this local time-accurate time stepping that we're doing with either DG results in some steps, more steps in some cells than others. It is becoming an impossible task. You need some help, and it's the best thing that a computer program will do. It's this runtime environment. So I like to put a word for that in the last bullet.
I agree, certainly with that. I mean, I think when we're talking about solving large linear systems, we should not necessarily think that that's a CFD-specific challenge, right? This is a challenge that's central to computational science in general. Things that I learned, I've had to unlearn many things that I learned in CFD over the years, right? Because packages get better and better at doing these processes for us, including parallelization. When I first started in CFD, the FFT was not, there was no FFTW library. And, so I went to program the FFT the first time, and I got out numerical recipes, and I wrote down the thing, and my advisor screamed at me and said, what are you, crazy? That's not nearly as efficient as you need it to be. Here's the way you do it, and he gave me some code and so on, right? But it was still this process of like CFDers trying to figure out how to write algorithms, right? The FFTW is far better than anything we ever came up with. There's no reason nowadays to write an FFT. And the same will be true largely of solving linear systems. There are just only so many kinds of linear systems, right? And there are a wide variety of techniques that are being improved very rapidly. So, I think this has impact on this question of large time step implicit versus explicit. But I do want to mention in that, just one other point in that specific topic, which is that we have to be aware that the physics also restricts the time step. And when we're talking about techniques like LES, there is no way to take a giant time step. Maybe there could be, maybe there are models that would allow that someday, but currently we have to track the CFL because we have to track the physics on that time scale. So implicit methods are very, very useful in LES, but not because they allow the use of gigantic time steps. They allow the time step not to be restricted by numerical difficulties with the grid, tiny grid cells that are unavoidable, and a host of other sins that we make when we grid problems and so on. So implicit methods are very important, but I don't think we should probably be thinking about giant time steps.
Tim, I subscribe to the notion that there are many operations that we use in CFD that are generic, and they're used by many other domains where we absolutely must use libraries that others are optimizing, FFTs, matrix multiplication, linear solvers. But in the spirit of giving the audience grand challenges of things that will be step improvements, even the DOE community that's working on things like PETSI will tell you that they yet do not know how they're going to scale the linear solver solutions or technologies they currently have to the 1 million plus course. So if you want a good problem, that's a good problem to work on as well.
Well, a couple of points there. So I think number one, anyone that's actually interested, if we have numerical methods here, we're probably interested in implementing them or experimenting with them. And I think if you don't know this already, like if you're not already checking to see, Googling to check to see what open source library is everyone, are the best people using to solve that particular problem. If you're not already checking that before you code, before you write one line of code, you're making a fundamental mistake. And one thing that constantly horrifies me is still the number of PhD students and researchers who are continuing to write their own iterative solvers and everything else from scratch, and it's what they're implementing is it's crap, frankly, because they're not really aware of the fact that already that there's specific programs like the PETSI I go back to again because I love the team there, but the people don't appreciate there's already been tens of millions of dollars like poured into like, you know, making these really, really good, and it's by a fairly large team of people, and this is the only thing they do in their life. And you're never going to beat them. And they're giving you putable interfaces that will scale on exascale, well, not exascale, but like, you know, petascale computers, and like will have every, like, you know, lots of Russian names that you won't be able to pronounce, like with different solvers and whatnot. And like, so as a starting position, like if you're implementing these methods and you're not using these libraries, well then you're doing it wrong, okay? And then if you're just doing it for fun, that you want to implement it yourself, well then recognize you're doing it for fun, but it has no intrinsic value. You're not moving, like, you know, science forward. You're not going to start up a company with this or that. So I think the number one step, I think, in terms of, before I get into something more esoteric or future-looking, I think we have to sort of state where the minimum bar is. Okay, so if you're not Googling what the best solution is before you start implementing something, you're already finished. You might as well give up. But like, you know, so and we're once again drawing the line under the fact that these things are open source. You can do what the heck you want. If you have a clever idea and create something new, you can start up a company and, you know, make it. So that's your starting position. But the other thing, getting more towards the end, then, is also looking for innovative ways of going forward. Okay, so again, like so I mentioned earlier on, like, you know, stop. If someone has already done something 30 years ago, like, you know, well, it's time that you should try and like do something new. But because actually thinking about the implementation process itself and programming, like, so basically, so if we take a historical perspective, up until the early 1950s, all software was written in machine code, and it was written for each specific machine, because you had to rewrite it for each specific machine, because each specific machine was unique. Okay, so like if we could fast forward now again to today briefly, we'll see we're pretty much in that position, right? We got GPUs, we got Xeon Phi, we got ARM processors, we got FPGAs, we got power series. Someone want to help me out, and now we've got a whole host of spatial computing architectures for deep learning coming online. So I'm sort of flagging that as one thing. This looks suspiciously like late 1940s, like early 1950s. And then it was in 1952, it was the very first compiler, like, you know, like A0 was invented for linear algebra. So they called it a compiler, but it was actually a DSL as well. And so this is Grace Hopper, so that's why the supercomputer in Lawrence Livermore, it's called Hopper. Yeah, and that was the first. Now, there was a lot of resistance. People were, I don't know about this. They actually called it automatic programming. And there was conferences called automatic programming at the time. And it was this radical idea that maybe you shouldn't be writing your algorithms in machine code. Maybe you can make life a bit easier for you. And then someone came up with the radical idea, that was 51, around 52, 53 was the first proposal for Fortran. And like IBM was pushing it hard, and the customers were saying, nah, like, I much prefer writing all my stuff in machine code. And it was 1957 before they released it. And then it was interesting because it was known as the first optimizing compiler, because that's the first time that the compiler technology and languages had evolved to the point that it was routinely developing better code than people that were handwriting it in machine code. And even then, people were still writing in machine code, like, you know, right up in the 1960s, still resisting, I don't know about these high-level programming languages, like, you know, Fortran. It's very suspicious. Now, the reason why I'm giving this history lesson is then fast forward to today. So we're in a position, like, number one, like that innovation happened 70 years ago. Okay? And you have to recognize, why did they make it? Like, ultimately, there was an interview, I forget the name of the guy offhand, like the original IBM guy. And this in the 1960s, in an interview, he was talking about why did people make the transition? Why did people stop programming machine code and went to something higher level to make the people more productive? And he said, well, people ultimately moved, not only because it was faster, that was a secondary concern, but because they were 20 times more productive. So I don't know where he got 20 from, but anyway, that's the quotation. So now fast forward to today. So now when we were faced with an explosion of different computer architectures, like, you know, GPUs and whatnot, like, so this was like in the early 90s, like, people start talking about CUDA. And so, like, I've got 20 years experience in HPC, where I've done the very low level optimization and all the rest. And then CUDA came out. So my attitude was, we're not being recorded, are we? Okay, so I have to mind my language. My students sometimes pull me up on this. Yeah, exactly. Someone got to beat. But my attitude was immediately, okay, look, this is the problem. We're struggling to train people to program, we're struggling to teach engineers and scientists to program well in Fortran and MPI and OpenMP, which is relatively benign and easy. Well, from a specialist perspective, comparatively, it's pretty easy. Now we have to get better at new conveyor architectures. So here's a solution: give people an even more verbose, an even more complicated computing language, and say that's the way forward. And then other languages like OpenCL or this. So I'm not embarrassed to say I think that whole philosophy in terms of going forward to HPC and to code modernization, frankly, I think it's completely stupid. Okay? I think fundamentally it's ignoring the lessons that were very clearly illustrated 70 years ago. They were very clearly understood at that time. It's totally ignoring, it totally forgets all of those lessons. And it's also ignoring the fact that today, the most important people, this is where I didn't agree with you with respect. The biggest mistake you can make is, if you're in science and engineering, is to think, oh, we'll just get some computer scientists and programmers, to do the work for us. The fact is, that is the source of some catastrophic failures and wastes of money in this. Because computer scientists and that, they might be very good in the particular, for whatever, Java, write websites, whatever. But the point is, what you're not really valuing here is that you have invested, depending on where you are in career, but you've probably invested 10 years of your life becoming an expert in the engineering in your domain, in your specific area, understanding the equations that you need to apply, and all the details of that. You have all of that knowledge. Guess what? Computer scientists and programmers don't have that. Okay, so they're not going to magically implement all your stuff, because when you actually sit down with them, I don't know if any of you have done this. I remember we got one computer scientist, we said, oh yeah, do blah, 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 and oh, this is for digital processing, apply FFT. A couple of days later, came back, what's an FFT? And this is a person who's a kernel hacker. He updates, he actually works on the Linux kernel. So you have to, just because someone is expert in one thing doesn't mean they're another. So this is a long-winded way of getting around to the point that I've taken the position, say historically I've worked on very large Fortran codes and C++ codes, and I'm efficient at optimizing these things for specific computers and so on and so forth. But a few years ago I completely abandoned entirely all of that area of work, and I just don't do it anymore. And largely it's because of focusing on DSLs. Because what we're doing today, and this is one of the reasons I've dwelled on it as well, is also one of the reasons I'm over, because we're discussing, this is another one of our collaborative projects that we're setting up with USP here in Shell, and we're doing this in another area for seismic imaging. So we're currently in a position, so let's go back to Juan's talk. So you asked a really interesting question. Who applied automatic differentiation tools? 2 hands went up exactly. So then you asked the 2 people, so what tools were you using? Both answers were the same, Dolphin Adjoint. What's special about Dolphin Adjoint is that it's all automated. So for those of you who don't do it, it basically uses a DSL, like UFL, so it's a uniform form language, and it does one thing and one thing only. It allows you to write down things in variational form for finite element. So it's very good at that. And it basically means with 1 line of code, a couple lines of code, basically enough lines of code that you can, you can read them on a single screen. You can already have a full-blown solver, and then you add an extra line and you've got the adjoint. And previously, this is what would normally have taken people 500,000 lines of Fortran, and then probably a team of PhD students to create the adjoint of it. So I think what I'm encouraging, I guess why I'm labouring this point so much, is you have to make decisions. If you're going to go forward, you're not going to go forward if you continue the way that people have been doing things for the last 70 years. Okay, let's innovate a bit. Okay, they've been doing it for 70 years. We can explore new ways of doing things. And you're not going to innovate if every time you want to add a term to your equation, you have to go and add 500,000 lines of Fortran. Okay, that's exactly why you see so little innovation in the large, this large engineering software companies, is because, I've talked, I can't actually say the names, but I've talked to, say the lead sort of developers some of these very large companies, like billion-dollar type companies, and they were basically saying like 99% of their developers are only maintaining the code, trying to stop the wheels falling off. It's not about adding any features. Now then, skipping forward then, what happens when you do things radically and say, is this all like up in the air? So currently in a project that we just started recently, and we're already in a position that like with a handful of lines of code, like in Python, we're automatically generating all their code. And to give you an idea of the complexity, the equation that we need to solve, it's a finite difference, like I think it's quite simple. But the equation that they want to solve, when you work out the number of floating point operations per stencil, you've got 2,000 floating point operations. If we actually, when the generated code automatically, if we print it up as a screen, you're talking about several screen folds just of solid text with the equations. And we also need the adjoint for doing it. But like it all comes from a single line of code. And what's more, then, when we were talking with industry and pitching our project, we were saying, well, like automation, you're not going to get that far. But like they actually bought into the idea only because we made their people more productive. Because it was very appealing that their geophysicists could write down one line of code, or they could just literally write down the equations. And that's what we tried to do with the DSL. We tried to get this one-to-one between the equation and the code that you write, and all this code magically happened, and they were sold on that. What no one would believe us is that we would actually beat the human programmers with highly tuned stuff. And the fact is that we do. Because people forget, like, you know, when you do engage, like there's other specialists in, once you engage them at the right level, we're able to start performing optimizations that are possible for humans to perform.
There we go. I'm going to put some caveats on it, Gerard. We know each other very well, so it goes fine from there.
That's because I can't stop them using C++.
Yeah, exactly. Well, so I've not been as big an embracer of splitting language or UFLs as Gerard has, so I often kind of question why that's been the case. I think one of the positive things that we should take from our earlier conversation is about not duplicating everything, and I'll definitely take that point. If there's a library or an interface mechanism where somebody's got the 500,000 lines of code, that's fine. I suppose one of the reasons is because I've tended to work in these high-order methods where there hasn't been the background and stuff. And actually, I've come back to your Petsy point. We have got interfaces to Petsy. We do find it useful to use, but it doesn't actually do all the things we need to do for our patterns. Now, I know we've talked to them and we'd like them to put it in. When we have these P methods, we have a sort of big H grid, and then we have lots of stuff underneath it. And that's a pattern that they weren't originally, designers weren't thinking of when they implemented the stuff at the outset. I know they would like now to do more high-order stuff. So don't be too completely disparaged if you find you have to write some of your own codes if you come from a different angle and it wasn't quite the same model as was there originally. I take a lot of the stuff that Gerard has said on finite elements and finite volume. It's much more well established. There's a whole load, a couple of decades of generations, and so you should look how best to utilize what's there and then carry on. And it falls very much into the idea we're saying earlier on, where do you use data and how do you use stuff that's out there and combine it together in the most effective manner. But maybe you'll have another idea, and if you find that doesn't fit into these patterns, then that forces you to have to go back to basics and build up each of these terms. So that's kind of where I hope why we don't always have to agree on these parts, but yeah, don't forget that part too. And if you're in that position, don't feel worried about the fact that you have to go and do the low-level stuff.
Well, I will change the subject and try to answer the first question. What is missing for commercial software to incorporate high-order methods? I asked that question to Sukumar Chakravarti, who is the guy that developed CFD++. And he told me that CFD++ has realizability concept throughout all the software implementation, which means it makes real. It means that for interpolation, for example, interpolation is not only a mathematical problem. If you obey the first law of thermodynamics, you are closer to solution. If you obey certain laws, conservation laws, you are close to the solution. So his answer is CFD++ is second order, but provides solutions with higher orders, which means with coarse mesh, it's close to the solution. So, answering the question now, I can say that there are other stuff to be done in commercial code before going higher order. If you have a bad software, it will be a bad higher order software. So they are concerned about other things. They are right now concerned about basic implementation, how to make accurate the turbulence models. For example, how to make wall distance free turbulence models, because the turbulence doesn't know the distance to the wall to happen. The flow is going here and become turbulent. The flow doesn't know the distance to the wall. Why our models has the distance to wall? So it should be other formulation. So they are saying that the models, the numerical methods, the implementation, but enforce the realization.
I feel like I don't answer about harder methods. Of course, I spent my whole career wondering why this point's not happening. I think there's a lot of inertia. You know, it's very hard to come up with just a pure logical reason for this. And the example when we talked about this the other day was for videos we had Betamax and VHS. And generally people thought that Betamax was a better format, but VHS survived. And so, you know, we've had decades of development in finite volume methods. There are 2 or 3 big commercial companies that don't want to suddenly lose their industries. Start CCM was bought by Siemens for $1 billion, and so you know, so it's not in their interest to kind of throw that all away and then start again. However, at the same time, open software and open foam, SU2, yeah. Oh, so yeah, sorry. Yeah, Juan will answer whether he thinks it's close to just with So the other thing that's happened for us in the last 5-10 years is open software has been able to build up a community and then it's really get involved, and that's probably the route by which we'll see these other things come into play. I feel. Yeah.
So let me just say 3 things. Open source is helping. It's largely focused on second order, but we're trying to sneak in higher order into the same environment so the customer base that's already adopted certain things may start looking at higher order methods as well. Let me say 2 things. One, just so we are all clear, I wouldn't say CFD++ is higher order. I think as we talked in some of the introductory lectures, they have a lower constant than maybe some of the other second order tools, but it'll still be a second order tool, regardless of what the developer of C++ says, CFD++.
In terms of the answer, the solution being achieved, it
has lower error.
Mesh convergence.
Okay, sure. It has lower error. It has a lower error constant, but it's still second order, regardless of how many realizability constraints they impose on that. But I have to say, though, that what I care about is the accuracy of the overall solution. I think both Tim and I made a point in some of our slides to say that there are numerical errors that creep in that can be addressed by going higher order in some situations, not always, right? And then there are a lot of uncertainties that come from the turbulence model. So in the aerospace industry, for example, there is a lack of interest in adopting higher order methods for standard problems because you're going to tackle the last, let's say, 5% of numerical error when you have 10% or 15% in the Reynolds average Navier-Stokes turbulence model, right? So you have to think about higher order in conjunction with the accuracy of the physical models that you're using to resolve problems. And I think whether one person goes one way or another depends on that joint error plus uncertainty. You see what I'm trying to say? If I'm a helicopter person and I'm really interested in blade-vortex interaction and I want to follow that vortex 3 revolutions before it hits the next blade, maybe I'm going to think that high order is a very good idea because the low order schemes are going to dissipate that vortex and give me the wrong interaction. But you know, if I'm trying to do a high-lift system on a full aircraft, then I may just choose to invest more effort in the turbulence models.
Yeah, I agree. There have been a few explorations and features when I've written this, and a student using higher order methods for RANs, and it's not clear to me that that's come out as being, yeah, this has to be the way forward. We've got perfectly good tools for that, probably because the error of the terminus model is consistent with the errors of the approximations. What's there to be gained? It's when we're changing the physics or asking new physics questions, or capturing or resolving LES, propagation of structures for many, many wavelengths, then it becomes very obvious that the higher order schemes are giving you a better solution and a quicker solution. Yeah. So it is, and it's because those problems are now coming to the fore and being questioned by industry that then we see the adoption or the interest in the type of schemes. So
but I think the point is that the future we should be encouraging and thinking about is the future where the CFD user has no idea, the user now has no idea what the order, quote unquote, of the code is and which which invariants it honors and so on. The code should be deciding which of those things are important in a given problem and applying them, right? So if you need extra accuracy in a given problem, because as Juan said, the code should give you an uncertainty. It should give you a plus and minus on every quantity. And if you're not happy with that plus and minus, the code can give you a more accurate answer by using a more accurate method, then it should do that.
And the code should decide for you
Absolutely.
how to allocate the computational resources you're willing to spend to get that higher accuracy between refining the grid, going to higher order in some elements in the grid, and refining the physical model if that's what it takes. So the grand challenge is for that automated management of errors and uncertainties together, right?
Shall we move to the next talk? Is that
No, just another bullet there. It's post-processing tools dealing with big data. And that's really, I'm in the market of post-processing tools because we institute TechPlot in Brazil. And they did a development that is subzone loading. They only load the part you are working. So it allows like, you load like a 2 billion cells elements in a 2 gig laptop. And it's 20 times faster. So there are technologies, some post-processing, they are parallelizing everything and working in a client server. So that's it.
I think you're a fan, to at least Peter Vincent is, but I think many ideas of in-situ processing are really, really good, and they've been around for a long time, and only now they're becoming more commonplace in post-processing and visualization software. But I mean, this idea that you're going to be able to load terabytes of data into a laptop, that's just gone. I mean, many of the simulations that we're going to be seeing for dealing with these problems we're talking about are going to require that you do something while the computation is running.
So,
Excellent. Yeah.
Okay, so let's start with hardware. So trained in massive parallelization architectures. Then we're going to speak something that the three of you have talked about. GPU processing, so we deliver what we promote talks is cloud computing, and maybe in this topic should comment on the typical computational infrastructure that academic or industrial CFD lab should have. It's like 6 years in terms of infrastructure that we use. So just implies the conversation asking you how much of your simulations nowadays are run in GPU. Zero team.
Yeah, relatively little. We have had some collaborations. It just comes back to this implicit-explicit challenge. So Mike Kirby, one of my collaborators, is UStar. There will be an NVIDIA GPU center, and we've looked at doing some of our tools on there, but we've not been able to get them efficient enough to overtake people with the semi-implicit stuff, just having the CPU environment. So I have questions, kind of like the DSL question, why, we've seen it there, I've seen a bunch of code development, why have we not done more of it? It's because I only felt we could benefit the explicit implementations at the moment, but our workhorse code for doing the semi-implicit formulations, and that's kind of been a bit of a barrier. I guess the languages are improving a bit more. I feel the time is right to do more of that implicit work that we talked about in the last slide, and then that will help our transition to the accelerators. There's no way these things are going away. You can see them coming. In a way, the two new American machines are the prototype. We've got IBM working with NVIDIA, and Cray working with Intel. So those are going to be the two biggest machines that come through, and they'll start populating our own countries, and so we need to work out how to adopt all of that. That's pretty much where I feel we're going.
To answer your question, in our lab we've been an Intel Parallel Computing Center for a few years, so we've been working mostly with Intel platforms, so CM5, KNC, KNL. Probably less than 5% of what we do is GPU, but we just started 2 months ago a collaboration with IBM. The existing architecture, Power 8 and soon Power 9, have NVIDIA and NVLink in it. So we'll have a version of the code in the next few months to a year that runs on GPUs. But I think more importantly than that, I wanted to make a point that unfortunately CFD or modeling and simulation in general is not necessarily driving a lot of the architectural choices that are being made. Some, they're paying attention, it's an extra market that they can capture, but I think we for a long time, I'd say the last 15 years, have been just forced to mold to whatever the prevailing winds are doing, and I think that's going to be the case for a while. So it's not getting any easier. I do want to say that I don't know if I was misunderstood before. I don't want to ship off or farm off our optimization to computer scientists, but computer scientists are doing a lot of work in order to make us a little bit less dependent on what platform we're doing by creating these runtime environments or by working with us to create the DSLs. In the runtime environments, they can know where in the machine you should execute something, but you have to tell them, and part of their programming language includes these constructs. You have to tell it what types of fields you're going to be accessing, are you reading or writing, how is it decomposed, and the types of stencils that you actually have. So I think the prevailing winds are going to push in whatever direction. We're going to jump onto whatever bandwagon comes along our way that can actually be used. But I think in order to do so productively, we really need the computer scientists working side by side with us to actually make this possible. Yeah. So that's the key, and they've been much more willing to do this in the last 10 years than they ever were before.
About GPU processing, I think something can be done with implicit methods when solving the linear systems. But to assemble the matrix, to calculate the terms to put in the matrix, I think it's too complex for GPU in terms of calculus or mathematical capability. And I think GPU has also poor access to memory, the main memory of the computer, not the GPU itself.
That's improving. Yes.
Yeah. No, right now.
Well, right now many of these GPUs go PCI Express, so it's bandwidth limited to the memory of the processor, whereas its device memory is much more readily accessible. But NVLink, for example, now provides a direct path that doesn't go through PCI Express, although it's still, a more remote memory and it takes more time. But I think we're going in that direction. I have to say we followed GPU processing from the beginning, and if you're complaining about CUDA or Gerard is complaining about CUDA, our computer scientists are mainly responsible for that. You gave a history lesson. I feel we have to tell you that Ian Buck, who is the main developer of CUDA, was a student in the second ASCII program at Stanford. Computer scientist sitting next to computational scientists. And they were doing something called Brook, which is a programming language to use GPUs when GPUs didn't have memory, and you had to use the texture memory of the device in order to do computations. So GPU, Brook GPU were the predecessors. NVIDIA hired him, and he took Brook GPU and turned it into CUDA. So, we're cursing him ever since.
I mean, we talked about algorithm check, but this is what will happen to get the things working, on linear algebra systems working on GPUs. One good example is we think of preconditioning as a kind of something over the whole mesh. If you can only load up a local part, why wouldn't you think of on a CPU would be good, but lots of local inverses there. Just do as many as you can afford to do, and then think about how you combine them afterwards. So It's that algorithmic attitude we have to change, and then we'll find the best solutions to go on with it. Maybe I can skip up or skip down to one question. How do you ask me how many people are using cloud computing? I could say we do have an interface to a cloud, whether that's good or bad, I don't know. But it's given us some experience of running. I guess we can run the 2D incompressible solver of the cloud and actually have some of the biomedical applications, which are not so compute intensive. We have been able to see that being quite useful. Up to the order of 100 cores, that's been pretty successful or reasonable scaling. So it kind of opens our eyes to say, well, you know, it seemed like it was just something for Java processing or ordering online, but there is good compute power there. Yeah, the speed of the network's improved. They have better machines. But Gerard and I have talked about this, and he perhaps wants to comment more, is why is our high scale, our HPC computing not so easy to use? And this is another massive barrier to how we go on to get other people to use these sort of facilities. It's kind of, it's an exemplar, yeah. So maybe I'll just let you carry on from there, Lord.
Tim saw me jumping up and down on the seat. He'll kick me this time if I start another rant. So in terms of hardware, so I think we sort of we got an introduction to how difficult things might get. I think with GPUs, but rapidly we're going into a world where it's going to get much more complicated. Like, you know, you already thought things were getting complicated before, but now they're going to really get complicated because we're talking about lots of more domain. We talk about domain-specific languages, but there's a massive and rapidly growing trend in domain-specific hardware, and this is particularly driven by the deep learning community. And so when you were saying about following trends, like the old days, like silicon graphics got killed off by the gaming industry on PCs. And then we said, okay, that now we must follow those guys. Now, going forward in the future with CFD, it'll be following the deep learning guys. So you'll be contending with like radically different looking processors, that like, you know, that don't necessarily have a Van Neumann type architecture. And it actually might, in some ways, it might be fantastic for CFD because they'll have a better balance between processing and access to memory. However, they mightn't have doubles in terms of flow. They won't have. They absolutely, nearly certainly won't have 64-bit floats. Most likely, they won't even have 32-bit floats. It's more likely that they'll have 16-bit floats, and then say, okay, well, if that's the architecture available to us in terms of bulk, how do we adapt our algorithms to that? That's a whole other question about algorithms. But the reason that I want to highlight that is because you were talking about, say, specific examples of innovations that we could do focusing on a particular hardware and a particular type of hardware, and I think that's the wrong way of thinking about it. I think what we have to think about, because we have an explosion in diversity, we have to think about how are we going to survive, like, you know, when every bloody computer starts getting exotic and much different from what we've seen before. So get back to Spencer's point, the reason I was jumping up and down is because I largely think that whole discussion is irrelevant. I think the discussion about quantum computing is a joke. Like, you know, it's a bit like nuclear fusion, right? It's going to be the energy source of tomorrow, and it probably always will. I think it's pretty much a similar joke for quantum computing. Like, it's always going to be like 10 years in the future. But I think the key point, and I think what you really need to focus on is usable computing. So literally today I don't care about flops or yada yada yada. That's good. That's stuff for the salespeople and geeks to get on about. But I think what you need to really think about, we all need to think about, is how is that making us more productive? Are we being more innovative? Are we getting the answers that we want? Because like the precious resource here is not the computer. Like, even if we get into supercomputer, buying a computer is actually relatively cheap, even if it's a supercomputer. Once you actually stack up the human cost. And like, you know, if you have to pay for a team of experts, and as someone was talking about earlier on, and they have to spend like a month playing around with CAD because they can't find where it's leaking, they can't mesh it, and so on and so forth. That's where you're burning money, and that's where you're not being productive. And I think we have to more start thinking about computing and supercomputing and everything else. Like, I think if it's user hostile, like that's just bad. It's bad design, and someone needs to fix it. Okay, and I think that's changing. I think one of the reasons then that cloud computing has been really disruptive is because it's made computing easy to use. It's made people productive. So I think certainly going forward, we're discussing with various other people now, like other supercomputer procurements, and I think more people are turning on to stop just focusing on the raw flops. Instead, we want to actually think about the flops that we're actually able to use today, not what we possibly might use for a benchmarking case, like sometime in the future, or some problem we don't care about. Productivity, humans is what's valuable. Your time is valuable. I don't care about about burning a few extra hours on a supercomputer. Who cares? Like, you're the person that's valuable, and your time.
Jim, do you want to comment something on this
one? Obviously, what's on the next slide.
Beers. Okay, so I'll move to the next topic. So next topic is CFD use. So a little bit less technical. Multi-physics simulations. So how to couple CFD with other computer-aided engineering software smoothly. How to use more CFD in science and engineering education. And how to make the use of CFD something closer to non-CFD experts and something that they can use without producing rubbish stuff.
Let's start with the last bullet. I think we talked a lot about it.
Yeah.
If I had to say something, is you really have to manage the errors and the uncertainties for the user to user-specified tolerances. And we've already said enough about what you might do about those things, but I think it's really important. I think the pre-processing elements of managing geometry and getting initial grids, et cetera, that also has to be part of that solution. And then the final thing is in the post side, is this interpretation, right? Or the warnings, or the expert systems. I think that has to be there. And until you have those three elements in the chain, you're not really going to be having proper use of CFD by non-CFDs.
In our company, we adopt a process that's you have three phases. One phase is the definition of the problem. You need to have some senior engineer to define the problem. You need to have experience to define the problem, to say, this variable is important, this geometry, this part is not important, cut that, in order to make the problem feasible and to provide the correct answer, because the problem may be too open, too spread, and it's not possible the solution in 2 months, in 3 months. So we have a process that we have a senior engineer and an analysis guy. It can be a fresh engineer or someone specific to run the CFD. And so you have geometry, mesh, and the solution after the problem definition that can be run by a non-specialist. And after that, you have the post-processing. And the post-processing, you need again a senior engineer to understand and to tell the guy, do it again because the result is not correct. And for me, it's incredible because in CFD world, we are not used to do hand calculations. If you go to structures world, the FEA, they do spreadsheets to check the calculation. And we don't do any hand calculations, and the problem become too open. You don't have anything to compare to sanity check. So you must do some sanity check before releasing the solution. Just that.
We're slowly wearing out. But so if I quickly do the next one up, because I think you also touched on that. It's not necessarily CFD in science and engineering education. It's just in general science and engineering education. That's the one that we talked about earlier on. We can see it across the board. then CFD will benefit, but I think in general we need to just get out of our molds of being a bit departmental and not thinking of computational science in this case being such an integrated part of our engineering education. So that's just got to happen. We've just got to get over our traditional barriers of departments and cost centers and that will explode.
Maybe with regards to education, we started a new class at Caltech in mechanical engineering 2 years ago. It's called modeling, and it's what used to be our experimental course, and what never was our CFD/CAD/FEA course. The idea is to do both physical experiments and computer modeling and put them together. It's been a real challenge. It's a 2-quarter class. I would say the biggest challenge has been to come up with problems that work rather than problems that don't work. And maybe that's a statement about the state of the art in CFD, but I think in terms of engineering, I think an over-reliance on we can get into sort of a dream box where we think that everything is just going to be predicted by computers, and we fail to recognize that those are real physical phenomena that we're trying to predict. And so I think getting those two things more closely connected in the curriculum would be a big help.
Maybe turn the question on the other way around, actually. What about the use of CFD in other classes? Not teaching CFD, but use CFD to teach other stuff. Wouldn't it help to make people more enthusiastic about it? For example,
I might weigh in again, and it's going back to the other point again about ease of use. Okay, and I think so. One of the other things, I think, again, harking back to the past, I think the old-fashioned way about thinking about how to build CFD technology, as in like the ANSYS solution, is that like CFD means open up this monolithic package that allows you to model rockets and cars and golf balls, all the same package. And then you just go into drop-down menu hell, when you want to solve a new problem, where you have got 20 menus that you can download, and each one of those things that you click, then you've now got 20 more menus that you fill with something else. And I think it has to be recognized that even in terms, so if you talk about can you make this available for non-users and introducing this in the teaching lab for other people, come on, it's going to take someone bloody months just to get used to finding where the hell do I find this option, through the menu for finding this new problem. I think it's silly to think that you're even going to do that. But we should learn from, from say modern software design. What does it look like? Your iPhone is not designed like that. When's the last time you read the manual for any application on your phone? And I think it's this contrast between designing these big monolithic end-user simulation platforms that have a massive computational, cognitive load. It takes you months to learn how to do it, even for doing trivial problems. And instead, what I'm advocating, and this is why I draw the parallels with mobile phone apps, is instead moving towards bespoke applications or customized solutions that are easy then to set up, where the student only has one thing to look at. So you have this thing and it does exactly one thing, and models flow past a sphere or whatever else. And then the way that I would advocate that this is being done in practice, so I'm not talking about a mad future like earlier on. I'm saying what an awful lot of people are doing now, myself included, is using tools such as Jupyter Notebook that it runs in your browser. So you can already do this with undergraduate. I do this with my first year geoscience undergraduates. And then you have they've all got their lecture notes inside this notebook, and then you've got a chunk of code that's Python, and it's calling out, it's running in a CFD solver or whatever, and they're able to interact with it, and it's showing the graph and the plots and everything else. And quite a lot of people now are starting to do this, and guess what? The students actually like it. It's easy for the students to follow, it's easy to understand. You can actually get somewhere over an 8-week program. You're not looking at just having a 1-year program just so they can find the right option in a big menu.
Can I say something? So I'm glad you ended your comment about the apps and stuff, because I thought you were going to say that we should program CFD solvers in a manner that is driven just like apps, and I was going to tell you that Candy Crush is always going to be a lot easier than solving the Navier-Stokes equations. But let me actually say one thing. When you ask how... Sorry? I was going to say though, for educational opportunities of CFD, my initial reaction to your question was going to be, no way. I teach applied aerodynamics, let's say, to first-year master's students, one of the fluid dynamic classes that I teach, and I much rather that they learn basic principles, trends, and for that, doing something that goes very, very quickly is important. So I force them to write a Hessman panel method, or a vortex lattice, or some boundary layer solutions, etc., etc. But then I remember that in my aircraft design class, we do use CFD in one area. We've taken a two-dimensional flow solver, SE2 version, and they don't even know they're running SE2. We put a Java application, and when you do airfoil design, and you do it in the transomic regime, where none of the applied aerodynamics simplified theories do anything for you, any of the scaling or anything like this. In those situations where there are discontinuities, shockwaves, etc., they actually run CFD, but they run it like an app. They say Mach number, angle of attack, or lift coefficient, and they say Reynolds number, and boom, you do it, and it gives you the CP distribution, the lift and the drag, etc., and they don't know they're running a CFD solver. But it's fast enough in those 2D settings that they can run not one solution, but 13 solutions or 15 solutions, and then they can establish trends and various other things. So I think in education you have to target things because it's still far too complicated to run something significant.
I guess I just want to add a couple of things about this. I think sharing of solutions and setups and solutions is absolutely essential. So, part of the problem with CFD is that we don't have one framework, one code, right? Where all the users are using the same thing, and they can just send the file over. You want to do a rocket? Well, here's the file for a rocket, right? You want to do granular flow? Here's the file for granular flow. But for whatever platforms we have, I think it's important that we set up mechanisms to share what we're doing. Something like the MATLAB file exchange, which if you're a MATLAB user, you must know intimately, right? Because when you want to do something in MATLAB, you don't think much about it. You say, oh, somebody must have thought to do this already. And 9 times out of 10, or maybe 99 times out of 100, that is the case, and you find exactly what you need. I think the other thing we have to keep in mind is that young people and even old people nowadays don't learn to use computers by reading manuals and by drilling every possible menu and seeing what they are and trying to decide what all those things means. I mean, I probably use in PowerPoint, I probably use 0.001% of the various features that are available to me, right? But they're laid out in a way such that I don't really need to know about them. I only need to know when I need to do something that I can't presently do. So we learn software by trial and error. We put it up, and if it doesn't do what we want, we say, why is it doing something? And we start poking at it, right? So, we move our mouse around to see what happens, right? We experiment. So CFD has to become a lot more like that. It has to prioritize the features in different ways than it currently does, so that you can quickly learn. If I want to solve for something, I should be able to pull up a file that's already done of something similar as possible to what I have, load it in, bring up some new options, and hit the run button.
I can talk about CFD++ because they are developing a new interface. I think it's 4 years from now. And they put some knowledge in the interface. Like they ask what kind of problem you are solving. Aerodynamics, okay. What is your free stream speed, velocity, such? You have 3 boundaries, which are the wall, which are the outer flow. Are you going to solve to wall or wall function? Which turbulence model would like to use. So your problem is set up. So you can put some knowledge, it takes time. They are working on that for 4 years because they have a lot of type of problems to deal with or to implement. But you know, that's a good idea. It's one step towards the use of CFD by fresh students or by non-specialists, because all the knowledge is the interface is a specialist system behind the interface.
I agree, we've also looked at the interfaces, but it's that last point that we already discussed earlier on, is how do you take specialist knowledge and make sure everyone doesn't have to keep relearning it and embed it in some meta information, or if it's there, or put the right constraints on your problem and say, no, I don't have an implicit solve, so let's not have a button saying you can solve this sometime implicitly, and then confuse people why that doesn't work.
You don't need all the boundary conditions for that problem.
Exactly. So
you don't need all the turbulence models for that problem. You maybe you need smaller Omaras, SST, and K-epsilon.
go on.
I'm going to argue now.
Okay.
I mean, with all due respect, I mean, I think what you're reporting for CFD++ is exactly the wrong way to do things, right? So, I mean, I know when I get a new software product, the most annoying thing in the world is when it wants to take me on a tour and ask me, to do this and do that and do that. I just want it to come up so I can start experimenting with the interface and it should be on a need to know basis, right? I should be the one that forces
The old interface is there also. You can use the one.
Okay, and just try to come back to the first point to finish our discussion. What about the integration with other software simulation? Do you think it can make it easier? Let's say that if you want to do some research interaction or a bit of heat transfer in your fluid simulation or compression simulation, let's say that. So, do you envisage any way of making it easier for software that you use? Maybe establishing a standard format for I/O?
So if you read the NASA Vision 2030 CFD report, there's a whole section that I wrote on it, on that question. And I think the answer is three things. One is what we call the plumbing of multi-physics simulation. So the basic infrastructure of exchange of communication between solvers that are representing different physics and that may be running either simultaneously or not, within parallel computers or not, etc., etc. So there's a whole aspect of facilitating multi-physics simulations that's that infrastructure, that plumbing, right? The second part of the solution, this is the most mundane, right? We think, okay, this is a solved problem, you just have to do the work. The second one, which is a little less mundane, but still pretty mundane, is the establishment of standards. As somebody said, we have lots of different CFD solvers, but there are lots of different structure solvers, and there are lots of different, thermal solvers, and various other things. So, thinking that if you have N, M, and L number of solvers and all these things, that you're going to actually have one-to-one connectivity between all of those is ridiculous. So you have to have some kind of standards for all of this, and that's advocated on for the CFD part in the Vision 2030 CFD report. But the most important part that comes along is that people think that if you have the plumbing and you have the standards and you slap these things together, everything's hunky-dory. And it turns out that if you have a perfectly second-order time-accurate fluid solver and a perfectly second-order time-accurate structural solver, and you don't do the connection between those two solvers properly, you can show mathematically that your order of accuracy in time automatically drops to first order or worse, right? So what we call the science of multi-physics coupling is really something that needs attention. And the plumbing of multi-physics coupling needs to be aware of the science of multi-physics coupling, such that he comes with a structural solver and I put a fluid solver, and very quickly we can actually couple them together in a manner that preserves the accuracy of the coupling solver. So there's some more things in that chapter, but those are my thoughts about it. And CFD needs to be more friendly towards being coupled with other physics, because when you talk about multi-phase flows, aerothermal structural track problems, fluid structure interaction, aeroacoustics, I mean, you can go on and on and on, and many of the pressing engineering problems today are physics.
Wants to make another point about it? So I think we can close the panel here. It's 5:30, so I'm going to the audience to give a round of applause for the